Question sound. All right. All right. We'll start. Good evening, all. So, can you confirm whether I'm clearly audible and visible? What about the audio and video? All right. It's fine, right? Okay, then we'll start without further ado. Okay, so we are at a point where you are like 18 days from the exam, right? You are 18 days from the exam, right? And the countdown goes on, right? Countdown goes on. We are 18 days from the exam, right? Just like 2 weeks and 4 days, right? 2 weeks and 4 days, very, very small time. And you know that decision about the postponement was also given today, right? So you know that is never going to postpone again, right? So if you are working throughout, then it won't be a problem. But if you didn't work throughout, right? And if you are trying to do this during last 2 months or 3 months or something like that, sometimes you might be struggling. But otherwise, since the dates were like already announced way before, right? So I think most of you are fine, especially if you are a first shy student. Sometimes there can be a student who suddenly decided to do the second shy again after results are out, right? Such cases also there. No? Now, in such cases, there can be some sort of a like time issue, right? If you are preparing for the exam after the results. But otherwise, for the others, if you have already, even though if you are a second shy or revision student, if you have already decided that you are sitting for the exam, for such ones, that won't be an issue, right? Okay, now, anyways, now final decision has came up and it is not going to postpone, no? Right? So keep up the good work you have been doing, right, for these 18 days also, and starting from 10th, right, just after 14 days, if you are doing main subjects, right, this whole story is over, right, just after 14 days. All right, so today about the essay practice session, I selected Madan radiation, right? Madan radiation, one of the reasons to select Madan radiation is radiation is a comparatively small lesson, right? And a definite essay is also coming. And since that is the last lesson we have, last unit we have in our syllabus, right? Sometimes most of the students are not that familiar and comfortable, right? Not that familiar and comfortable with lessons like matter and radiation, electronics, right? Magnetic fields, because they are towards the like last end of our syllabus, right? But yet, when it comes to a question like, especially a question like matter and radiation, that is comparatively a manageable and a convenient and easier question as well, right? With less number of theories, less scope, less area, right? And we know matter and radiation question is coming as an elective with thermal question, right? So compared to thermal as a unit, right, matter and radiation is like 1/5 of thermal, like 20% of thermal. 20% of thermal, what we are doing in thermal, like 1/5. But yet it stands for 30 marks. Right? That advantage is there. So that's why I have selected this. Right? So let's see how it goes. I will recall the background theories that I'm using when you are doing the questions. And other than that, you will be practicing how to write this. And I have uploaded this to the Telegram and the Google Drive, right? And the links are pinned on the live chat, so you can go there, and if you didn't get the questions yet, you can get it from there, right? And I uploaded these questions in the afternoon, right? If you have already tried, you can check your answers with me, or if you have any clarifications, if you need any clarifications regarding the questions you tried, you can check, right? And others, if you didn't get the questions yet, you can go there and get it downloaded, right? We'll start. All right, then without any further ado, we'll start. Let me share my screen. All right, you can see the screen, right? I hope you can see the screen. Right. So I'm going to start with the last year question, right? And since that is about black body radiation, right? If I quickly recall the theory part, right? The theory part here about black body radiation, right? It is like this. Black body radiation, right? Black body radiation is given under two main theories, right? One is called Stefan's law, right? First one is Stefan's law, right? And the next one is Wien's law, Wien's displacement law, right? Wien's law, that is also called Wien's displacement law, Stefan and Wien. And Stefan equation is like this. Stefan's equation is, right, Q over T. This is also written as E over T. Fine. Q over T is sigma A T to the power 4, right? Stefan's law. Where Q over T is, power of heat radiation, right? Or simply Q is total energy of heat radiation, then T is time, then Q over T gives the power of heat radiation, right? Sigma, Stefan's constant, A area, right? Or perpendicular area, then T, absolute temperature. And Wien's displacement law is like this. That is about, that is a relationship about lambda and T, right? So what it says is lambda T equals K in backward radiation. Lambda is corresponding wavelength or respective wavelength for the maximum intensity, right? When we draw the curve or I lambda characteristics in the I lambda characteristics curve, right? I is I M means so this is what we draw as a I lambda characteristics, right? Lambda M is here. So this is about this lambda M, right? Wavelength corresponding to maximum intensity, right? That is called lambda M, right? Actually, that is lambda M. Then as an equation, right? What is coming from Wien's law is lambda 1 T1 equals lambda 2 T2 if you are using the equation for two different scenarios, right? So otherwise, lambda MT equals K, and K is called Wien's constant. K is called Wien's constant, right? So basically, black body radiation is given on these two, right? That is given on these two, and other than that, for the energy calculations, intensity calculations, power calculations, right? Other than these ones, equals ida is also used as an equation. Equals ida equals ITA, right? We call equals ida, right? Then intensity is given by E over TA, right? Intensity is given by E over TA, right? That is one form of this, and or else we can keep the same equation as E over T is IA, no? E over T is power, then power equals IA. P equals IA, right? So these are the equations that we'll be using in this part, right? So let's see how it goes, right? Let's see how it goes, right? Then first question. It says, right? It says, right, straight away it's starting with a question. What is the value of surface emissivity? What is the value of surface emissivity of a perfect black body, right? Now, about Stefan's law, right? We have something like this about Stefan's law. In Stefan's law, for any kind of a black body, not a perfect one, not an ideal one, perfect means ideal, right? For any kind of a black body, that is defined as this: Q over T equals E sigma A T to the power 4, right? Where this E is called, right? If there is none ideal, this E is called surface emissivity, right? Where this E is called surface emissivity. If there is none ideal, surface emissivity. And this E is a value between 0 and 1. E is a value between 0 and 1, right? So basically what it gives is, right, how close that to a black body, how close a body to an ideal black body, right, in terms of this, right? That's the idea. Then for a normal body, E can be any value from 0 to 1, right? If E equals 1, we call such bodies black bodies. If E equals 1, we call such bodies black bodies. Then first question is about this, right? So what it asks is, what is the value of surface emissivity of a perfect black body, right? E equals 1, right? E equals 1. Second one, assuming the sun as a perfect black body, find the surface temperature of sun that emits radiation as at a peak wavelength of lambda max 500 nanometers. Take Wien's displacement constant as 3 times 10 to the power minus 3 meter kelvins, right? Then if only one scenario is given, then directly we can apply this as lambda T equals K, right? Wien's displacement law, lambda T equals K, right? Then we need T, lambda is given 500 nano, right? 10 to the minus 9, 10 to the minus 9 into T equals K, Wien's constant. Wien's constant is given 3 times 10 to the power minus 3, right? 3 times 10 to the minus 3. Then T is given by 3 times 10 to the power minus 3 over 500 times 10 to the power minus 9. Then T equals, right, 30 over 5 means 6, no? Right? 6. Then that is, this is 10 to the power minus 7 minus 4, then 6,000. 6,000 kelvins. 6,000 kelvins. Right? 6,000 kelvins. Next one. Part 3. Calculate the power radiated per unit area, I, of the sun. Right? Power radiated per unit area. I of sun. I means intensity. Power per unit area means intensity. Sigma is given, right? Sigma is given. Stefan's constant is given, and take 6 to the power 4 as 1,300. Right? See how many hints are given to you to apply, or to you to guide towards Stefan's equation, right? All hints are also given, right? All hints are also given. Then apply Stefan's law. Now it is considered as a perfect black body. Then E equals 1. So we know Q over T equals then sigma A T to the power 4, right? And if we need it to per unit area, then that is Q over TA. This is also written as E over TA sometimes, because Q can be written as E, right? And that is sigma T to the power 4. This is called I, intensity. Then that intensity is, that is coming from this equation, equals eta. E over TA is I, know, right? E over TA is I, know. Then Q over TA is also I. Q over TA is also I. Q is because that is a heat energy, that is a heat radiation energy. That's why Q is put, right? Otherwise, just by considering it as an energy, we can use E also, right? Then sigma is given 6 times 10 to the power minus 8. 6 times 10 to the power minus 8, right? And T is 6,000 to the power 4, right? Now use these given values accordingly. This is 6 times 10 to the power minus 8, and this is 6 to the power 4 times. Now here you have a 10 to the power 3, no? Then 10 to the power 3 to the power 4 means 10 to the power 12, right? then this value is given. 6 to the power 4 is given. 6 to the power 4 is given as 1300. Right? Then the numbers to be simplified 6 times. Right? And here 1300 10 to the power minus 8 12 means 10 to the power 4. Right? Then simplify it. 13 into 6 means 78. Right? Then final answer 7.8. Final answer 7.8 times 10 to the power 7. 7.8 times 10 to the power 7. Now, this is an intensity, this is in Wm minus 2. Right? That is in Wm minus 2 because that is an intensity. Right? See, very straightforward. Very straightforward. Knowing kind of a small theories, small means a small scope of theories, right? Still you can manage. 4. If the radius of the sun is r, write down an expression for the total power radiated by the sun in terms of I and r. Right? Total power. Right? We know P equals power can be written as IA. P equals IA. Right? I recall the equation before starting also. P equals IA. Right? Then I is considered as I it says, and radius of sun is r. Then you have to put the total area, total perpendicular area of sun, right? Area of sun is a spherical object, that is a sphere. Then area is area of a sphere. Area of a sphere is given by 4 pi r square. Then that's it. P is I times 4 pi r square. I times 4 pi r square. Right? Then 5. Assuming that the surface of the earth is at a distance d from the center of the sun, write down an expression for the radiative power received per unit area S as earth surface at the earth surface in terms of I, R, and D. Okay, then something like this. Sun is somewhere here, right? And from the sun, earth is located d distance away, right? Always heat radiation travels in all around directions, right? Any heat radiation travels in all around directions, right? That is not a linear distribution, that is an all around distribution, right? So that distribution is, or the spread is spherical. Therefore, always when we find these values at a distance, you have to consider this spherical distribution. You have to consider this spherical distribution, right? That's a spherical distribution. Then from this total power, right? From this total power, the power that is going to receive here is given as S, no? Power received per unit area. Power received per unit area, S. Yeah, power received per unit area. Then S can be written as power received per unit area. Then total power radiated by the sun is total power radiated by the sun is I times 4 pi r squared, no? Then per unit area means divide this by the area. Then total area of this distribution or the distributed sphere is 4 pi d squared, right? 4 pi d squared. 4 pi to 4 pi cancels off. Then S equals, right? We can keep this as r over d complete squared I. R over d complete squared I. Right? So see how easily you can manage this, right? Now we are like halfway through of the question, right? In no time. 6. A calculation based on that. See, a direct calculation based on that. Then if d equals 250 r, calculate the value of S. So we know S is this. Then r over d is 250 r squared. I, right? Start. I we found, no? What was the I? 7.8 10 to the power 7. 7.8 10 to the power 7. 7.8 10 to the power 7. Right, then simplify this. R to R cancels. R to R cancels, right? And this should be simplified now. 1 over 25. It's a simplification now. It's a small simplification. Then this is 25 means 625, no? 625, 10 to the power 2, right? 7.8, 10 to the power 7, right? Small simplification. Do that simplification. As the final answer, we are getting 1248. 1248, right? That is also an intensity power per unit area, Wm minus 2. 1248, right? A small calculation based on the proved equation in the previous step, right? Moving on. B. Part B. Part B. A solar sail is a spacecraft propulsion system, right? Now it's a creative part given with a kind of a story, right? Read the story and understand the scenario, and answer the given questions. A solar sail is a spacecraft propulsion system. It uses the radiation pressure of sunlight to propel itself, similar to a sailboat using wind, without requiring fuel for that. Light photons bounce off the reflective thin sail, transferring their momentum to the spacecraft, not causing it to accelerate over time. And causing it to accelerate over time. The shape of the hexagonal solar sail is shown in figure 1, right? Figure 1 is given. The solar sail is made of a light material and the sun facing side is coated with metallic material, typically aluminum. Okay, some kind of a explanation is given. What do you mean by wave particle duality? That's a theory part. What is wave particle duality? Right, wave particle duality. We know any sort of matter we have in this world, right? Any matter has two behaviors, right? Matter either behaves as uh, particles or it behaves as waves, right? That behavior is called wave particle duality, right? So what do you mean by wave particle duality? Then write down the property of matter, the property of matter which behaves either as a wave or a particle is called wave particle duality, right? Is called wave particle duality. That's a straight theory part. Second one, what nature of the wave is used to explain the motion of the solar sail? What nature of the wave? Right. Now it says it is using photons, light photons. Photons means they are particles, right? Photons are particles. Then the question is what nature? Then particle nature. Particle nature. Right. Third, derive an expression for the momentum P of a photon in terms of energy and speed of light. Hint, use the relationship of energy of a photon to its wavelength and de Broglie equation. Right. See, a hint is also given. Right. What else to be given? A hint is also given. Then from photons we know energy of any photon is given by E equals hf. Right. Then F can be expanded as CO lambda because C equals F lambda. Then E is HCO lambda. Right? E is HCO lambda. Right? Then say this is one. From de Broglie's equation we know lambda equals H over mu. Mu is momentum. Right? Lambda equals H over mu. Now linear momentum is given. It is given as P. Then we can write this as lambda equals H over P. Right? Then derive an expression for momentum of a photon. Right. Then we have to remove lambda now. We need just the momentum. To remove lambda, we can use this. Then from 1, lambda is hc over e. from 1 lambda is hc over E, right? From 1, get the substitution from here. From 1, lambda is hc over E, right? hc over E. Then hc over E is h over P. H cancels. We need an equation for momentum, right? We need an equation for momentum. Then subject P from the equation. Subject P from the equation, P equals E over C, right? See how easily we can get those, right? See how easily we can get those, right? 4. Hint is also given. In the hint, all the equations that you need to use are also given. Then just combine those two equations, right? Just a matter of combining the equations. That's it, right? Just a matter of combining the equation, right? 4th one. NASA has designed a spacecraft with a solar sail of effective area 500 square meters. The power received per unit area on the solar sail by the sun is 1200 Wm minus 2. Calculate the force exerted on solar sail by the incident of photons using the expression derived in B3 above. Right. Assume that all photons have the same energy and the photons are incident perpendicular to the surface of the solar sail and recoil backwards without changing the magnitude of momentum upon the incidence. Speed of light is okay. Now, one hint is given that it recoils back. It recoils means it reflects back with the same velocity, right? With the same velocity, right? Which means change of velocity is going to be, or the change of momentum is going to be, right? Doubled, no? Right? If you have no idea about that, right? This is what happens. It is going to recoil with the same velocity. Now, after hitting on the surface, say delta mv, then that difference is like m times, right? V minus u, final velocity minus initial velocity. Initial velocity is also in the opposite direction. See, it recoils back with the same velocity. It recoils back with the same velocity, right? Recoils back with the same velocity. Say it hits from this side, right? Side doesn't matter. Say it hits from this side, from initial velocity v, and it comes back with same v. Then final velocity is v, initial velocity is minus v. That is opposite. Then it is 2mv. Then as a momentum, that is 2p. As a momentum, that is 2p. That is one idea you should have, right? That is one idea you should have before getting the start, right? Then we can find total energy here, right? Total energy on this what we call it, solar sail. Total energy, total incident energy, right? So we know total energy can be written as total incident energy per second, per 1 second. Total incident energy per 1 second, right? Then total energy per 1 second is power, no? Right? So we know power is given by IA, right? We got the equation before also. Now this I is 1200 and area is 500, right? Then that is also known. Then to find the force, we know the relationship between force and momentum. What is it? The popular equation coming in mechanics, F equals delta mv over t. Then change of momentum. Change of momentum is 2p now, right? Time is 1 second now. Then 2 times p, right? For p, you have proved an equation here. What was it? Maybe p is E over C. Then you can write this p as E over C. Then 2 times E is here 1200 into 500. C is given, right? Then 3 times 10 to the power 8. 3 times 10 to the power 8. Right? Now, a matter of simplifying this. Right? Simplify it. And that is 4 times 10 to the power minus 3 newtons. Right? So you can give it as 0.004 newtons. right? See how we use that proved equation for the question asked, right? And delta MVOT is coming from mechanics, right? That is connected. That is coming from mechanics, right? So likewise, can go on. Likewise, can go on. Next, part 5. Part 5. If the total mass of spacecraft mentioned in B4 above is 400 kilograms and starts at rest from the International Space Station, how long in days will the spacecraft take to reach the moon, which is at a distance of 4.05 times 10 to the power 5 kilometers away from the station? Give your answer to the nearest integer. Assume that there are no other forces acting on the spacecraft and force exerted on the solar sail is constant throughout the journey and the equal to the value obtained in B4 above, right? Okay, that is equivalent to that 0.04 now. Then first of all, if mass is known, you can find the acceleration, right? So we know F equals ma. Then force is 4 times 10 to the power minus 3. Mass is 400, right? 400 A. Then find the acceleration first. Find the acceleration first. That is 1 times 10 to the power minus 5, no? That is 1 times 10 to the power minus 5 ms minus 2. Acceleration is known. If acceleration is known, to find the time it takes, use a linear motion equation. Use a linear motion equation. S equals ud plus half AD squared. S equals ud plus half AD squared. Right, then S is given 4.0.5 times 4.0.5 times 10 to the power 5 kilometers, then 10 to the power 18 meters, no? Right, u is 0 initially at rest, then half acceleration is here, right? 1 times 10 to the power minus 5 t squared, right? Then 4.05 into 2 means 8.1. Then 8.1 times 10 to the power 8. 8.1 times 10 to the power 8 equals, this is 10 to the power minus 5 t squared. 10 to the power minus 5 t squared. Then t squared equals 8.1 times 10 to the power minus 13, right? 8.1 times 10 to the power minus 13. 85 and 13. Then this can be written as, see, that's coming with the perfect root. This is 81 times 10 to the power, sorry, minus me plus me, 10 to the power 12. 81 times 10 to the power 12. That is 81 times 10 to the power 12. Then we need t. T is 9 times 10 to the power 6 seconds. Right, now time is known in seconds. In seconds, right? You ask that in days. Then in days, right? Therefore, in days equals, this is in seconds, 9 times 10 to the power 6, right? One day is 24 hours. 1 day is 24 hours, and 1 hour is 3,600 seconds, right? Simplify this. That is 1 second, 24, 36. That is 104.16. That is 104.16. Right? You are asked to give it to the nearest integer. Right? You are asked to give it to the nearest integer. The nearest integer is 104, then 104 days. Right? It takes 104 days. 104 days. Right? See how easily it is manageable if you know these things. Right? Theory is mugud dannadu, but if you know the theory parts here, right? It's a manageable question. Right? Then 6, right? Part 6. Why are the sun-facing side of solar sails coated with aluminium? Right. Now there is an open question. That you need to answer just by your knowledge. right? Now, initially it gave that it is coated with aluminum, right? Now, what is used to absorb energy here is reflection, right? What is used to absorb energy of photons is reflection here, right? It was given at the beginning, that is reflection. Then to increase reflection, to enhance reflection, right? It is coated with aluminum, right? To enhance reflection. Then to increase, so you can say enhance, to increase the reflection of, to increase the reflection of incident, increase the reflection of incident photons on solar cell, incident photons on solar cell, right? To increase the reflection, or to get the maximum reflection also you can say, or else to get maximum deflection, maximum reflection, or to get maximum reflection, right? That's an open one, right? You have to think at that moment and answer. 7. Figure 2 shows a cross section of a solar cell fixed to a spacecraft. The direction of the incident photons is shown in the figure. Copy the diagram onto your answer sheet and draw the direction of reflected photons and the direction of thrust on the cell exerted by photons. Okay. Then if the solar cell is like this, right? If the solar cell is like this, right? If the solar cell is like this, right? Now we know this is a normal drawn to that point. No. Now the incident ray is this. Incident photon means incident ray, right? Always, as angle of incidence equals angle of reflection, right? It is reflected. As angle of incidence equals angle of reflection, right? Then this is the reflected photon. Reflected photons, right? And momentum change, right? Direction of momentum change. Direction of momentum change. Now, when it is hit from this direction, right? When it is hit from this direction, components are coming in the rightward direction. Components are coming in the rightward direction. So the push is rightwards. Push is rightwards, right? Since that push is rightwards, right? That force is rightwards. That force is rightwards, right? The push is rightwards. Force is rightwards. And the direction of thrust, then this is the thrust. This is the thrust. Right. See, that's it. So in no time, we have scored 30 marks, 30 out of 30. In no time. Now for the explanation also, I think I took like 30 minutes only for the explanation. But when you are doing this question by your own, right? If you got everything at once, like in 15 to 20 minutes maximum, 15 minutes or 20 maximum, you could complete. Right. So that's it for the first one. That was a combination of black body radiation basically with the wave particle duality, a small touch with wave particle duality, and equals ida, P equals Ia, right? Those equations. Right. Any questions? Can you show fourth and fifth again? Show means you are asking me to show the screen. Just now I joined. How long did I miss? Check the timeline of the live video. Right? Check the timeline. If you miss something, just go back. This is a YouTube live video, no? Go back and check what you have missed, right? And if you miss a calculation, just go back and check it and complete it and come back from there. Right. Give me 1 second. I need to bring my charger, right? Sometimes I might run out of battery. That is 36 now, right? So give me 1 minute. I will bring the charger and we'll come back. Give me 1 minute. All right. Anything else? Anything else? You can ask and get clarified if there's anything to know. Right? Anything to know means any clarifications needed. Right? Especially the clarifications from the question we discussed. Right. If it is clear, we can move on. Right. And as the second question, I have chosen 2024 question. Right. That is a X-ray production. Right. So we know. Right. We know. Give me 1 second. Right. We know. When it comes to demonstrations, two main demonstrations we have. In this lesson is demonstration of photoelectric effect and the demonstration of X-ray production. Right. From both questions are kind of popular. Right. So since that has a exclusive theory part, right? Otherwise, when it comes to X-ray production, no uh, photoelectric effect or laser production, those ones, right? You can't just think what's happening there and we can't answer, we can't write, right? So therefore, just go through the respective theory part and get it familiar to yourself and be comfortable because there are only two demonstrations, right? I'm going to make a theory පොඩ්ඩයි තියෙන්නේ මේ පාඩමේ theory පොඩ්ඩයි තියෙන්නේ. Theory පොඩ්ඩයි තියෙන්නේ මේක manage කරන්න lazy. When we have kind of a small scope of theories, that is easily manageable. That's a benefit. Right. So let's see how this goes. X-ray production. I will recall again how this production goes with the question as we are moving through. Right. Let's see. The figure shows a schematic diagram of X-ray tube. It operates at V 30 kilovolts, and the filament current is 4 milliamperes. Okay. Now, basically, what happens here is, right, I'll quickly explain how this X-ray production happens, right? So what happens is due to this battery, there's a current circulates through this filament. Right? Then a high voltage supply, due to this, a high voltage supply is given between the anode and cathode, right? This is called the anode, that is the target, and this is called the cathode. Cathode is the filament, right? Because of that high voltage supply, electrons which are passing this filament are ejected from the wire and attracted towards this side. And because of the high voltage supply, they gain a massive acceleration, they gain a very high acceleration, and it travels towards this target. And they hit with the target, they collide with the target, they collide on the target, right? As soon as it collides on the target, what happens is its total kinetic energy, right, is immediately lost. Its kinetic energy is immediately lost. When that kinetic energy is lost, right, what happens is heat radiation comes out. Right? When that kinetic energy is lost, heat radiation comes out. With that heat radiation, right, photons which shows the properties of X-rays are also coming out, right? And here as a ratio, usual ratio is there's 99% of heat and only 1% of X-ray photons, right? So with that ratio it comes out, and that's how X-rays are going to produce. Right? So basically this is what happens in a X-ray tube. Right? Basically this is what happens in a X-ray tube. Right? So basically this is what happens. Right, now let's get into the question. Right, since this diagram is not clear with these drawings, I'm erasing these drawings. Right. Right. Let's see. Okay. Now, this was a given data. This was a given data here, 30 kilowatts. That is important when we are moving on, as we are moving on. Right. Then this is given as 30. This is given as 30. Right. 30 kilowatts. Right. This is given as 30. Right. Then first one. See, first one. Determine the number of electrons n hitting on the target per second. Electron charge is 1.6 into the minus 19. Right. So we know, right? We all know current is defined as Q over D, no? Right? Current electricity. In current electricity, current is defined as Q over D. Current is defined as Q over D. It is also written as Ne over D using charge of electron. Charge of an electron, Ne over D. Right? Then apply this. Current is given 4 milliamperes, 4 times 10 to the power minus 3. I need N over D. I need N over D. Charge of an electron 1.6 10 to the power minus 19. Right? Then N over D is given by right? 40 over 16 means 2.5, no? Then 2.5 10 to the power 16. 2.5 10 to the power 16. Right? Second one. Calculate the total kinetic energy K of all electrons hitting the target per second. Assume that the initial kinetic energy of electrons emitting from the filament is negligible. Right? Total kinetic energy from electric fields we know. Right? Now the equation is coming from electric fields. From electric fields we know W equals Q delta V. Right? W equals Q delta V. W represents kinetic energy. Then kinetic energy is, right, Q delta V. Then from one electron, this is per second, right? Target per second. Okay. Then even though that is about energy, so what you are actually going to get is a power. Kinetic energy per second, no? Right. Then for one electron, E, right? Say delta V is delta V. And there are N number of, or N over T number of electrons hitting per second. Then E is 1.6 10 to the minus 19. And delta V, potential difference, was given as 30 kilowatts. Then 30 kilowatt 10 to the power 3. N over T we found as 2.5 10 to the power 16. Right? Per second, no? Right. Then simplify this value. Right? It is simplified to 120 joules per second. 120 joules per second. Right? Or else you can keep this answer as 120 watts. Or else you can give it as 120 watts. 120 watts. Right? Third one. Out of the energy calculated in A2 above, 95% of is converted to heat in the target metal. This generated heat is taken out using a copper rod covered with a spiral copper tube connected to running motor. Right? We call that evacuation. Right? In X-rays we have discussed under theories. That is called evacuation. Evacuation process. Right? Evacuation using a rod. Right? Then running motor, calculate the mass rate M in kilograms per minute. In kilograms per minute of flow of water if the temperature increase of water is 57. Take the specific heat capacity of water as 4,000. Right, 4,000, not 4,200 now. 4,000 now. Okay, then see, now this is connected to thermal. Increase of temperature of water. Then Q equals ms theta. Q equals ms theta. Right? Q equals ms theta. Simple as that. Q equals ms theta. Then if you need this per second, right? Per second, since I have the value of power per second, per second value, even though this is kinetic energy, this is actually energy per second. This is actually energy per second. Then we can divide this both sides by T. Then here power is created. Then power equals, I need M over T, right? Then S theta. Apply in the equation, then power is here 120, but only 95% is utilized. Then 95% of this power, right? I need M over T. S is 4,000, right? 4,000. Theta is 57. Right? Simplify. simplify. 0 to 0 cancels, right? 12 times 95 and 12 and 4 also cancels, no? Right? We'll simplify this way. By 4 this cancels. This is 4 times 3, right? 4 times 3 and this is 4 times 1000, right? Then M over T is this is 3 times 95 over 57 should be given for a reason, right? This number might be cancelling with 57, we'll see, right? 3 times 95, right, over 10 to the power 4 here, right? 10 to the power 4 here, 10 to the power 4, 10 to the power 4, 57, right? Then what's the value there? Yeah, 3 times 95 is 285. This is 285, right? It cancels off now. 285, that is 10 to the power 4, 57, no? 10 to the power 4, 57. This is exactly 57 times 5. Then this is 5 times 10 to the power minus 4, and this is in kilograms per second now, because I have the value of power here in seconds. But what we need is per minute value, no? Then convert this to per minute. Convert this to per minute. And if this is the per second value, 5 times 10 to the power minus 4 into 60, right, will be per minute, right? Then per minute. 3, no? Then that is 3 times 10 to the power minus 3. 3 times, sorry, 10 to the power minus 2, 300. Then 10 to the power minus 2. That is 0.03 kilograms per minute. 0.03 kilograms per minute. 0.03 kilograms per minute. Right? A normal Q equals MS0 calculation. A normal Q equals MS0 calculation. Right? So I got M over T per second, then convert it to per minute. Right? By multiplying by 60 per minute. Right. Next. Part B. So likewise, when a number like 57, right, that's not the whole number. No? When something like that is given, right, always you should get an idea that it is given for some reason. So it might be cancelling with a number here, right? Always when you simplify with that idea. Simplify with that idea, right? B1. Calculate the minimum wavelength. Calculate the minimum wavelength, lambda mean of the emitted X-rays. Planck's constant is given and speed of light is given. Okay, minimum wavelength, no? So we know equals hc over lambda, right? Equals hc over lambda. Then equals hc over lambda. And this energy is due to, right? E delta V, right? After calling equation that is due to E delta V, right? Then energy is E delta V hc over lambda. Simplify. E 1.6 10 to the minus 19. Delta V was 30 kilovolts. 30 kilovolts at 6.6 10 to the minus 34. Right? C 3 times 10 to the power 8 over lambda. Right? So that's a simplification. Simplify this. Right? That is 4.125. 4.125 times 10 to the power minus 11. Right? Energy is due to potential difference, right? That equation is coming from our electric fields, right? That is coming from the electric fields, right? And we know energy of a photon is written as HO lambda. Energy of a photon is HO lambda, right? Combine those two, right? So we have lambda, right? This lambda is given as lambda min for the minimum energy, no? Lambda min, right? Then part 2. Does the lambda min value calculated above depend on the target material? Give reasons for your answer. No, because lambda depends on, right? Lambda depends on Lambda depends on this energy, right? Lambda depends on energy, right? Energy of photons. To increase energy of photons, what you need to change is potential difference. If you need to increase the energy of photons, have to increase potential difference. Otherwise, nothing with the metal. Check with the equation also, right? And there is no. That's a no, right? So write down. Minimum wavelength. This is unlike photoelectric. That's why this question is asked, because in photoelectric effect, lambda and frequency depends on the metal, right? But in X-ray, nothing such. Right? Minimum wavelength depends on energy of photons. It varies with potential difference. In the language of X-ray, we call this accelerating voltage, right? Potential difference, or in the language of X-ray, that is called accelerating voltage. Right? With potential difference, accelerating voltage only, right? So that's a big no. Third one. If the filament current increases, does the lambda min value calculated above change? Give reasons for your answer. Still no. Because, see, what happens is when the current increases, now go to our first calculation. See, when the current increases, the impact of current is to N over D. So when current increases, number of photons hitting the target per unit time increases, right? When the current increases, number of photons hitting the target per unit time increases, but yet energy of a photon is unchanged. When current increases, right, there's a impact. There is an impact, right? A special impact and a very important impact on the setup. That is, when current increases, NOD increases. NOD means number of photons hitting the target increases. When that increases, X-ray production increases. Higher the number of photons hitting on the target means higher production of X-rays. Increases, but not the energy. Only the production increases, right? Then the explanation is, right? Give reasons. Give reason for your answer. Then when current increases, this is the explanation. When current increases, only the number of photons collides on target per second increases, right? Right? Now, for your knowledge, you just know that when that increases, what happens is X-ray production increases. Right? X-ray production increases. Only the production increases. But yet, kinetic energy remains unchanged. Because my point is, kinetic energy depends only on the potential difference, right? Equation kinetic energy depends only on the potential difference. That's the point. Kinetic energy depends only on the potential difference, right? Then 4. The target metals are usually made of tungsten or molybdenum. What are the reasons for this? Right. Molybdenum is not that popular, but tungsten is popular. Right. About tungsten, we discuss usually in the theories also. Right. Now, what happens here is when electrons are collided, I told you there's a very high heat radiation comes out. Right. Like 99% of heat is 99% of energy is converted to heat. Right. So it is its temperature increases rapidly. When the temperature increases rapidly, if the melting points are comparatively smaller values, the anode metal or the target metal will be melt, no? Right? If there are small values, the target metal, anode metal will be melt. Then in such metals that is used in X-ray production, right? Their melting point should be very high. Their melting point should be very high, right? So reason is that melting points of these metals is very high, right? Melting points are high, right? Melting points are high, right? Then part C. That's another part. X-ray beam of intensity 5 times 10 to the power 3, Wm minus 2, right? Intensity. Wm minus 2 is incident on a human organ with an effective surface area of 0.01. Calculate the total energy delivered on the organ in 1 second. Total energy in 1 second means, right? Power, no? Power equals IA, right? Abhi. මේ equation එක කලින් දිගටම use කරා. We have been using the same equation in the last question also. IA. Now I is given 5 times 10 to the power 3. 5 times 10 to the power 3. And area is 0.01 10 to the power minus 2. Then that is 50 joules. Right? 50 joules. So 50 joules per second. Right? That is asked. In 1 second, in 1 second 50 joules. In 1 second 50 joules. Right. Second one. If the mass of organ is 0.5 kilograms, calculate the absorbed dose in gray. Right. 1 gray is given as 1 joules per kilogram. 1 joules per kilogram, no? 1 gray. Then here we have 50 joules. See, when you convert, you have to convert this. Right. Here you have 50 joules. Right? How many kilograms? 0.5 kilograms. 0.5 kilograms. Then that is 100 joules per kilogram, no? Right? Which means 100 joules per kilogram. Then joules per kilogram means 1 gray. Then 100 gray. Right? A normal conversion. Just a conversion. Then third one. What is the best material that can be used to? What is the best material that can be used to effectively block or shield X-rays? Right. That is an open question. Right. That is an open question. Right. What is the best material that can be used to shield X-rays? Right. Now in the X-ray production tube also, right? So what we are using is tungsten. So tungsten is one. In the X-ray tube also, right? As a shield, we use tungsten. Other than that, right? Concrete is also used, right? Right? Sometimes you might have heard about the nuclear disaster in Chernobyl, right? So in such disasters also, right? In such disasters and other nuclear disasters also, when there are dead bodies are buried, right? When the dead bodies are buried on ground, right? What happens is, what is done is, right? It is covered with a very thick concrete layer, right? That is covered with a very thick concrete layer to minimize that radiation. To minimize the radiation comes out. X-ray is also radioactive, right? So that's used when radioactive samples are buried, right? So concrete is also one. Tungsten, no concrete. And there can be other materials as well. These two are the popular ones. Right? There can be other ones also. 4. 4.1. Why it is important to measure the effective absorbed dose of radiation in sieverts for people working in radiation environment? Right, what is measured in sieverts? Right, we discussed in the theory. Sieverts. In sieverts, health risk of being exposed to radiation is measured. Health risk of being exposed to radiation, that is also called the biological risk or biological impact of radiation. Health risk, right? Biological risk, biological impact, right? The reason is the absorbed dose, right? Absorbed dose can be different, right, from the absorbed dose, right, or the effective dose. Effective dose and absorbed dose can be different. Absorbed dose is what matters, our biological side or the health risk, health side, health impact. Then these two are two different things. That's why that is measured in sieverts separately. That's what you need to explain. Right? What's the question exactly? Why it is important to measure the effective absorbed dose in radiation in sieverts? Right, working in radiation environment. Right. Then the effective dose, right? Effective dose and biological dose, biological or impact, biological impact depends on the type of radiation, exposed. Right? Now, sometimes effective dose can be same, but with the type of radiation. As an example, say someone has exposed to X-rays and another person has exposed to gamma rays and another person has exposed to alpha rays, right? And another person has exposed to cosmic rays, right? Different types of biological impacts, right? That's why another separate unit is there as sieverts to health to measure that health risk or the biological impact. Biological impact is also called the health risk. Biological impact is also called health risk if you need it, right? That is also called health risk, right? About sieverts we discussed in the theory parts, right? Second one, what might be the reason that the effective absorbed dose vary between different types of radiation, even when the absorbed dose is the same, right? So that's what I told you, right? That's what I told you. It depends with the type of radiation, right? To measure it, we have something called Q factor in this radiation industry, right? So Q factor is different. Or you can say Q factor is different, or the biological impact or the biological absorbed dose is different from the type of the radiation, right? What might be the reason for the effective absorbed dose vary between different types of radiation? Then Q factor changes from Q factor depends on Q factor depends on the type of radiation. Q factor depends on the type of radiation. Q factor depends on the type of radiation. Q factor depends on the type of radiation, right? That depends on the type of radiation. So that's what I explained before, right? Exposing to alpha is different from exposing to gamma, right? Exposing to another type of radioactive element is different from exposing to cosmic, right? So likewise, it's different. Part D. Now, when it comes to this question is a little bit lengthier one compared to the previous one we did, right? a little bit lengthier, right? D, when an atom is struck by a high energy electron, an inner electron can be ejected, creating a vacancy in the energy level. An outer electron can transit to the vacancy, emitting a photon with energy equal to the difference between energy levels. This process can generate X-rays with definite frequency. We call this, right? Discuss kara in theories. We call this process of ejecting an electron is linear spectrum of X-rays. Linear spectrum, right? We call this linear spectrum, right? And there was another one called continuous spectrum. This is about linear spectrum, right? So likewise, connect this with the theory. It's this process can generate X-rays with definite frequencies. If the energies of higher and lower levels are E1 and E2 respectively, the frequency f of emitted X-ray photon is given by HF equals E1 minus E2. Equation is also given, right? Energy is given by the difference, right? Then E equals HF. Here H is Planck's constant. First one. For aluminium of E1 equals minus 74 and E2 equals 1624, calculate the energy in electron volts of X-ray photon emitted when electron transmission occurs from higher energy level to lower energy level. Right, then delta equals energy that is E1 minus E2. E1 is, what about E1? E1 is minus 74. Minus E2 is minus 1624. Right? Then that is 1550 electron volts. 1550 electron volts. Right? Equation nothing to do. Second one. Determine the corresponding wavelength of X-ray photon produced. Wavelength. Hc is directly given 1240 eV. Right. In electron volts, that is given. Then determine the corresponding wavelength of X-ray. Then the equation was given as HF equals E1 minus E2 is delta E now. Right? So HF is written as HCO lambda. Can be written as HCO lambda. That is delta E. Delta E is known and Hc is given. Right? I'm going to plug that value without converting. Then we'll get the lambda also in nano. Right? We'll get lambda also in nanometers. That is given in nano. Right? Then Hc is 1240 over lambda equals, this is 1550. All right. So lambda is given by 1550 over 1240. Right. Simplify this. Right. That is exactly 0.8. 155 over 124. No? 155. Sorry, other way around, right? 124 over 155. Right. See, then lambda is 124, 1050, 0 cancels. Then 124 over 155. Yeah, that is simplifiable. That is 0.8. Which means that is 0.8 nanometers, because we plug this value in nanometers. We plug the value of Hc in nanometers. So that is 0.8 nanometers. Right? E. How do hard X-rays and soft X-rays differ from each other in terms of energy, wavelength, and penetrating power? Right. That's a theory question again. Right. We have discussed about two types of X-rays produced in this X-ray tube: hard X-rays and soft X-rays. Right. Hard X-rays are the X-rays with higher energies, higher frequencies. Right. Higher energies, higher frequencies equals HF. No. Higher energy, higher frequency. Then how do hard X-rays and soft X-rays differ from each other? Then energy. About energy, what you need to say is about energy, right? Energy of hard X-rays is higher. Energy of hard X-rays is higher compared to soft X-rays, right? Have to write in words as a sentence. You can write down. I'm just giving you the idea. Then about wavelengths. Energy ka danna frequency ka mata we know equals HF, right? We know equals HF, no? Then higher energy means higher frequencies. Higher frequencies means lesser wavelengths, because frequency and wavelength is always inverse. Then about wavelengths, about wavelength, the opposite of this. Hard has a smaller wavelength, shorter wavelength than soft, right? Wavelength is opposite because E equals HF. Then, and penetrating power depends on frequency. Yeah, penetrating power depends on frequency. Higher the frequency, higher the penetration. Then penetration, right? Penetration. Now about frequency we know equals HF. So about frequency we know equals HF, no? About frequency we know equals HF. Then higher the frequency, higher the penetration. Higher frequency is for hard X-rays. Then hard is higher, soft is lesser. Right? Penetration depends on frequency. Penetration depends on frequency. Right? Higher penetration, higher frequency. Right. That's it for the second one also. All right. Any questions? Any questions about the second one? Any questions about the second one? Will both black body radiation and X-ray come together or separately in different years? Depends. It depends, right? Sometimes there are questions like from X-rays you are given for like 20 marks, and from a radiation part 10 marks, right? Combinations are there. Right? Combinations are there. So if you are planning to take this question, right, what my advice is, you have to know all the theories, right? That's a only small scope here, no? Right? Only a small scope. Taggala meka padam karaganna puluwan. Edi konda padam karagana, and since that is connected, anything and everything connected in matter and radiation, right? And it can be easily connected as well. And the other thing is, it has some connections with lessons like thermal also, right? Q equals ms theta, Q equals ml wage equations වලට යන්නත් පුළුවන්. But just about matter and radiation, everything is connected. It's starting from quantum parts for quarks, leptons, nuclear binding energies, nuclear reactions, right? Radioactivity, radiation, black body radiation, then photoelectric, X-ray, right? Everything is connected. Separate rods. As a guessing, what is more prominent to come this year? Just study the last 10 years, right? Just study the last 10 years, right? The idea, right? And there was a pattern before in the questions, right? There have been a pattern in the questions before 2019-20. There was a pattern, but now slowly that pattern is kind of breaking, right? That is actually broken by the professors, because otherwise, when students know the pattern exactly, because there has been questions from X-ray and photoelectric year by year for many years in the past, but now those patterns are kind of breaking and they are deviating. So questions are deviating from the pattern. If you study last like 5 years, 6 years, right, we don't have any visible pattern in the questions, right? But easily manageable questions with the things you know, but we can't pinpointly say whether it's X-ray or photoelectric or something like that. Now, since last year has been black bodies, right, and the previous year is X-rays, right? Now an essay from photoelectric has not been come, then photoelectric enna puluwan, and potential parts are photoelectric, right? Potential parts are photoelectric, right? And nuclear means nuclear binding energy, age determinations, age calculations, right? And other than that, nuclear binding energy calculations, nuclear equations, nuclear fission fusion reactions, right? So those parts are kind of having a potential. And repeating again, anything and everything can be connected easily, right? It can be connected very easily, right? So anything else about the question we discussed before we move on to the next? Anything else? Anything else? So as the next one, I have chosen 2019 because in that one we have a age determination, a nuclear reaction, age determination, right? Those parts, right? මොකද in question එකක් ටික දවසකින් ආවේ නැහැ ටික දවසකින් කියලා කියන්නේ. Now it has a potential to come, right? So I selected 19 with some different approach in the 19 one, right? Any other question? So is it clear enough? And if you are planning to do this question, right, definitely you have to try the questions in last 10 years. Try last 10 year past papers, right? Practice them and see the types of questions you have got, right? See the types of questions you have got in last 10 years and get the idea and go to the exam, right? No need to worry. Easily you can write, right? If you have that idea, right? The manga these are 3 questions out of last 10 in last 10 years, 25, 24, and 19. Practice other questions also. All right. And I couldn't tell you at the beginning. I'll be taking tomorrow for the discussion of Western provincial paper, right? Western provincial paper, right? I'll be discussing Western province paper tomorrow, right? And I'll be finishing the classes tomorrow at like 10 p.m., right? 10:15 so we can start like 11. I didn't share the flyer yet also, right? I will share the flyer. It'll be happening 11 p.m. tomorrow, 11 p.m. onwards, right? 11 p.m. onwards. We'll do the discussion there, right? Western provincial paper, right? So discussions are coming up, right? And you can get all the updates through the channels, right? Check the channel and turn on the notifications and check the channels. And when I put a message to the channels or the groups, right, check it and you can join on time, right? So I'll be starting at 11 p.m. tomorrow, right? 11 තමයි ගන්න වෙන්නේ ක්ලාස් ඉවර වෙන්නේ 10:15 වගේ වෙනවා, right? ඊට පස්සේ 11 වගේ start කරමු, right? Okay. Western provincial paper, if you have already tried it, you can join the discussion with your doubts, right? If you haven't tried it, I will send you the paper. If you don't have, I will send you the paper. Try the questions and join the discussion, right? 2019. Read the following passage and answer the questions. Radioactivity of a spontaneous radioactivity of a spontaneous decay process by which an unstable nucleus becomes a stable nucleus by, right? Since the passage is going, right, I'm just skimming through the passage, right? Just skim through the passage, right? And if there's any important data, you can highlight, right? 1 Curie is equal to this, right? Then Curie and Becquerel conversion is given, and then another equation about lambda is given, right? And okay, Right, I'm just skimming through. And here half-life is given. Half-life time of iodine 131 is 8 days. Okay. Then let's go to the questions. Right, questions වලට ගිහිල්ලා ඊට පස්සේ message එක බලන්න. So as you go with the questions, right? As you go with the questions, you can check the passage. You can skim through the passage. How long is the essay discussion? You mean now? Right, this is the last question we are discussing. State two differences between the emissions of beta and gamma. Right. So we know beta is a particle. And gamma is a electromagnetic wave. That is electromagnetic wave. Right. Then right, mention these differences. Beta is a particle. Beta is a particle. And gamma is an electromagnetic wave, or you can say electromagnetic radiation. That is electromagnetic radiation or electromagnetic wave, you can say. Electromagnetic radiation or electromagnetic wave. Okay. Then two differences. Okay, we need another one. Right, we need another one. So we know about beta. Beta is what has happened? One second. Okay, anyways. iPad is kind of heated. I'm on the charge now. Right, charge again got screen share karla Zoom meeting charge is heat now. Right, for some reason it has stuck now. Right. Okay, then beta is 0, -1, and gamma is 0, 0. No, gamma is 0, 0. Atomic numbers and mass numbers, that we know, right? That we know. Then when beta emits, we know with this -1, atomic number changes. Right? And when gamma emits, atomic number is unchanged. That is also a difference, no? Then second difference here is atomic number changes. Atomic number changes when emits. Atomic number changes when emits. And here atomic number remains unchanged when emits. Atomic number remains unchanged when emits. Right. Second one. And also about beta and gamma, you can say gamma is highly penetrative. Penetration of gamma is high, right? This is high penetration. High penetration. This is low in penetration, right? You need any two. High penetration and low in penetration. You need any two, right? Right. Second one, rewrite the following decay equation replacing ABC with correct numbers. Okay. Then iodine 131, 53. Right. Xenon 131, A is given. And beta is a known particle. No? Beta 0, -1. Then 0, -1. Balance the equation. To balance the nuclear equation, right, there should be an equal number of nucleons at both sides, right? Atomic number represents number of photons here, number of protons here, and mass number represents the addition of sum of protons and neutrons. Then here in this side there are 53 protons. Then to balance this, it must be 54 here. Then 54 -1 is 53. And check the mass numbers, 131, that is okay. Then answers for these three are A equals 54, B equals 0, C equals -1. Right? Then part B. A fresh sample of sodium sodium 131 iodine having an activity of 100 millicurie is received by a hospital. The sample is stored in a lead container at room temperature. In a lead container at room temperature, right? What is the SI unit used for activity? SI unit of activity is becquerel, right? That's a theory part, no? Becquerels, right? Becquerels, BQ, becquerels. Write down an expression for the decay constant lambda in terms of half-life time. A proved equation. Right? That is a proved equation. Right? That is a proved equation. Using half-life time, no? Then lambda equals 0.693 over T half. This is a proved equation. Lambda equals 0.693 over T half. Third one. Or else you can write the same equation as, right? Or else you can write the same equation as ln2 ln2 over T half. Right? Both are fine. 3. Calculate the activity of above sample after 4 days and express the answer in SI units. Take ln2 as 0.7. Right. Now they have given that 0.693 to take it as 0.7. Right. Now only we can assume that as 0.7. Right. Now we can assume that as 0.7. 0.7. And e to the power minus 35 is 0.7. Okay. Then after 4 days, no, then we know for activity, we have an equation like this. For activity, R equals R naught. We can write it as either R or A. That's fine. R equals R naught e to the power minus lambda D. Right? E to the power minus lambda D. And we need R after how many days? After 4 days. After 4 days. Then R equals R naught is given. R naught was given as 100. No? That is 100. 100. E to the power minus lambda. Lambda is 0.693 over T half. Then 0.7 is given. And T half. What about T half? T half was 8, no? 8 after 4 days. Then R equals 100, right? E to the power minus, right? 8 4 means 2 remains, then 0.35. See, this value is given. 0.7. Then R equals 100 times 0.7. R equals 70. Now this is in millicurie, right? Now you are asked to convert it into SI, right? You are asked to convert it into SI. SI units again, and the conversion is given. See, conversion is given. 1 curie is equal to 37 times 10 to the power 9 disintegrations per second. Disintegrations per second is called becquerels. Right? Disintegrations per second is becquerels. Right? Then to convert this into becquerels, multiply this with this number. 1 curie again. Then here I have, right, this much of curies, milli. Right? This much of curies. Then R equals 70 milli 10 to the power 3, 37 10 to the power 9. Right? So that is 2.59. 2.59 10 to the power 9. Right? Becquerels. 2.59 10 to the power 9 becquerels. Right? Conversion is also given. Right? Okay, 3 is done. Then 4. Right? 4. Hence, express the change in activity as a percentage. Right? Then we know any change is written as final minus initial over initial value, no? Then final value was 70. Right? Final value was 70. Then about this. When we write final minus initial, we know these are decay. These are about a decay. Then final value is a less value. Then you are getting a minus sign. To exclude that minus sign for the change, you have to put another minus sign since there is a decay. Right? Minus sign means decay. Or else, when it comes to radioactive decay, if you are writing a difference, right, you can consider initial minus final. Right? Both fine. Right? Both are fine. Then initially it was 100, no? Finally 70. Initially 100. Then percentage into 100. Right? Then what's the change? Change is 30%. Change is 30%. Change is 30%. Change is 30%. Right? 5. Is it possible to reduce the activity of sodium sample if it is stored at 0 degrees Celsius instead of storing at room temperature? Explain your answer. No. Very straightforward, because radioactivity, right? Radioactivity does not depend on any external factors, right? It does not depend on any external factors. It depends only on the initial number of radioactive particles in the sample, right? So simply radioactivity is independent of all the external conditions, right? It is independent of all external conditions. Temperature is also one such condition. Temperature, pressure, wind speed, humidity, right? Nothing. It depends on nothing. Then 5, no. Reason, radioactivity. Radioactivity is independent of external environmental conditions. Right? Next, part C. A small amount of sodium iodine sample having an activity of 100 millicurie is administered into a thyroid patient. First one. The thyroid patient. When dealing with such a patient, for which mode of emission the radiation protection measures should be taken? Explain the answer. For which mode of emission? Right. Now, we know from here, from the one here, right? In the description it was given, right? See, about penetration length, it is given. About gamma photons, and the maximum tissue penetration length of beta is 2 millimeters. The half-life time of patients of sodium iodide, that is called sodium iodide in the form in a capsule once administered, it's absorbed into the cells. The answer is here in the passage. Kills most of the cancer cells. Okay. Then compared to beta, right? Compared to beta, gamma has a higher radiation. Compared to beta, gamma has a higher radiation. Then we have to protect from gamma. Because penetration of gamma is high. Then what's the question then? When dealing with, okay, the radiation protection measures should be taken for which mode of emission? Gamma emission. Then gamma emission. Right? Then explain the answer. Explanation is in the description. Maximum penetration is for gamma, and beta has a less penetration, so it won't come out the body sometimes. But gamma comes out. Then explain. Penetration of gamma is higher than beta. Penetration of gamma is higher than beta, right? Higher than beta. So that gamma might come out the body. After penetration. Right? So I got this from the passage. Read the passage. Second one. Show that the effective half-life time Te of iodine 131 in thyroid gland can be given by 1 over T equals, okay, can you remember that one equation was given for lambda? See, it is given that lambda equals lambda p plus lambda b no plus lambda b, right? We know lambda is we know lambda is 0.693, or it is considered as 0.7 now, over t half no, 0.693 over t half, 0.7 over t half. Since we are asked to consider it as 0.7, now we can consider it as 0.7. Then lambda e can be written as 0.7 over te. Lambda p is 0.7 over tp. Lambda b is 0.7 over tb. This cancels off and this remains. See how easy? 1 over t equals 1 over tb plus 1 over tb. That's it. Right? Easily gettable. Third, if the biological half-life time, that is TB, yeah, that is in the passage. If the biological half-life time of iodine is 24 days, calculate the effective half-life time of iodine in days. Right. Now, this was given. Listen. See, the half-life time of iodine is 8 days, and somewhere here in the passage it says corresponding to physical. Then physical half-life time is, right? Physical half-life time is TB, right? Corresponding to lambda p, and biological is B. Then physical is given as 8, no? Physical is given as 8. Then applying the equation equals 1 over physical is 8 and biological is now given as 24. Biological is 24. Simplify. Then 1 over t equals 24. This is 3 plus 1, no? Then t equals 6 days. Right? 6 days. Again, a small calculation. Then fourth one. Calculate the percentage change in activity after 4 days of administration of iodine 131. Take e to the power minus 0.46 as okay. That answer is also given. Similar calculation as we did before. Right? We did something similar before also. So, right? Similar calculation as we did before. Right? You have the same idea from the previous calculation also. R equals R naught e to the power minus lambda t. We need R again. Initial value is 100. E to the power minus lambda. Right? Lambda is 0.7 over, right? T half. Now half life is 6 days. After 4 days, no? Into 4. Right? After 4 days. Into 4. After 4 days. Right? Simplify this. Now, when you simplify, you should know that now if 0.46 of E is given, you should get that number somewhere. No? Then check that number whether you are getting it. Because if you are getting it, means we are done. Otherwise, if you are not getting it, you are following something wrong. Simple as that. The idea is sitting done. So this is 2 and 3, no? Then this is 100 E minus 1.4 over 3. Right? 1.4 over 3. Check that number. 1.4 over 3 should be that given value. 1.4 over 3. Yeah, that is exactly 0.46. 0.466. So 0.46 is given. Right? So this is minus 0.46. Nothing to do now. This value is given. What was the value? 0.63. Then this is 100 times 0.63, which means 63 millicurie. 63 millicurie. Calculate the percentage change. Right. Then change again. We did a similar change calculation before also. Then change is given by, initially it was 100 minus now it is 63. Initial value is 100 into 100%. 100 cancels off. Right. Then 37%. Percentage change. Right. See. Percentage change is 37. Right. See, again in a no time, in a quick time. See how many marks we have got now. More than 25 marks for the question are already taken. More than 25 marks for the question are already taken. Right? 5. Around 26, 27 marks are now taken. Right? 5. 5. According to radiation protection regulations, iodine 131 treated patients can be discharged from the hospital when the activity is below or equal to 50 millicurie. 50 millicurie. If the regulation is followed, how long the above iodine 131 treated patient has to kept in the isolation in the hospital before discharging? Right. So at once, if you can see it as 100 to 50 means that is half, no? Right? Easiest way is this. 100 to 50 means that is half. That is half. Right? What is the meaning of half-life time? Half-life time is a time it takes to halve the number of nuclei in a radioactive sample. Half-life time half-life time is the time it takes to halve the number of nuclei in a radioactive sample. Then if there is half, then it should take a half-life time. Then it should be 6 days. If you didn't get it at once, applying the equation and still you can get the answer if you didn't get it at once. But otherwise you can easily get it just by the half-life time, the definition of half-life time. So we know this can be written as R equals R naught to 2 to the power n, right? Make equation. Then finally this must be 50. In this equation, n is number of half-lives. In this equation, n is number of half-lives. Then Rho is 100 over 2 to the power n. Simplify. 2 to the power n equals 2. Then 2 means 2 to the power 1. No? It says n equals 1. N here is number of half-lives. If anyone who don't know the equation, n is number of half-lives. Right, then one half-life has gone. Right, so therefore it must be 6 days. One half-life of iodine is 6 days, no? 6 days. 6 days. Right? Then how long? 6 days. How long it is? 6 days. According to the radiation, okay. 6 days. Right? So if you didn't use the equation, you can say, right? Equation you have to explain this. If you didn't use the equation, you can say, since effective half-life time of iodine, 1 second. Temperature is very high here. That's why this is stuck. Okay. See. Where was I? Now it's visible, no? Right. Where was I? Here. Effective half-life. Since effective half-life of iodine 131 is 6 days. Right. Since effective half-life of iodine 131 is 6 days. Right. So that's it. That's it about that question also. Right. See, I have discussed 3 essay questions, right, from 3 recent years. 3 different types of questions. 3 different types of questions. Right. And see, what I wanted to show you is, right, this is something that you can do with a less theory part, a small theory part. Right. I make a heady. This is something you can easily do with a small theory part. Right. In a quick time. Right. So therefore, you can gain an advantage, you can get an advantage if you are comfortable with the lesson, right? You can do it in a quick time. Easily you can do, right? Quick time and 30 marks. right? Compare you have to compare this with the thermal question, no? Thermal only make 20% lesson. Right, that's the thing. Okay, any questions from these ones we discussed? Any questions? You can ask if anything before we wind up. Can ask if anything before we wind up from the things we discussed. Anything? Is it clear enough? Is it clear enough? Okay, seems no questions now. Right. Right. Listen. Listen. Right. Okay. Right. So what I'm highlighting again is when it comes to matter and radiation, right? That's a lesson that you can do with a small theory part, right? Small theory part. So practice all the questions in last 10 years minimum. Last 10 years minimum if you are planning to take this question, right? And I'll be taking another session for essay practice for properties of matter also. Properties of matter also. So probably next Thursday we'll be having that session, right? So you can practice such questions before you go into the exam, right? More and more types of questions you know, more comfortability you get, right? That's the thing. So don't think of the time you spend with these things these days. This is the investment you do for the entire life that is coming up, right? Don't think of the time you spend. Don't think of the strain, fatigue. Don't think of the effort that you put, right? You might be exhausted. That's how it is, right? We are also exhausted. You are also exhausted. But think of the future. Think of the investment that you do here, and practice these questions, right? Then if no any questions, we can wind up, right? We can wind up. And as I told you, tomorrow we'll be having the discussion of provincial paper of Western Province, Western provincial paper. I'll be taking to the discussion tomorrow, right, at 11 p.m. All right, then, if no questions, we'll stop here, we'll wrap up here. Then work hard, and practice these questions hard. And if any questions, anything from my side, you can contact me. All right, then. No questions, right? Then I'm going to wind up, right? See you in the next session or next class, right? Stay safe and work